Quantum particles are fascinating for several reasons, starting with their ability to exist in multiple states simultaneously through a phenomenon known as superposition. Unlike classical particles, which occupy one definite state at a time, quantum particles like electrons can be in a combination of different states all at once. However, once you observe or measure them, they collapse into one definite state. This is a defining difference between the quantum world and our everyday experience. Another key difference between quantum particles and classical particles is their ability to act like both particles and waves, depending on the situation. Light is a perfect example of this dual nature. Photons, which are the particles of light, sometimes behave like discrete packets of energy, called quanta, but they can also act like electromagnetic waves. This is known as wave-particle duality. A famous demonstration of this is the double-slit experiment, where particles like photons or even electrons pass through two slits and create an interference pattern on a screen, something you'd expect from waves, not individual particles. However, when we try to observe which slit the particle goes through, it behaves like a particle again, and the interference pattern disappears. This shows how the act of observation itself influences quantum systems. One of the most well-known principles of quantum mechanics is the Heisenberg uncertainty principle, which states that you cannot measure both the position and momentum of a quantum particle with perfect precision at the same time. The more accurately you know one of these values, the less accurately you can know the other. This principle challenges our intuitive understanding of measurement and shows just how different the quantum realm is from the classical world. Then there's the mind-boggling concept of quantum entanglement. This is when two particles become linked or entangled in such a way that the state of one particle instantaneously affects the state of the other, no matter how far apart they are. For instance, if two entangled particles are separated by light years, measuring the state of one will instantly determine the state of the other, even across vast distances. Einstein famously called this spooky action at a distance, as it seemed to defy the limits of communication and the speed of light. While this may sound like science fiction, it's a real phenomenon that has been experimentally confirmed. However, an analogy using twins living similar lives, while fun, doesn't quite capture the mystery of quantum entanglement, which happens instantaneously and is more profound in terms of its implications for communication and understanding of the universe. Some examples of fundamental quantum particles include electrons, quarks, which make up protons and neutrons, photons, and neutrinos. These particles follow the strange rules of quantum mechanics. In total, there are 17 fundamental particles in the Standard Model of particle physics, which include quarks, leptons, and bosons, particles that mediate forces, like photons for electromagnetism or gluons for the strong nuclear force. Another intriguing concept is Schrödinger's cat, a thought experiment that illustrates the oddness of quantum superposition. Imagine a cat in a sealed box with a vial of poison that could be released based on the decay of a radioactive atom. According to quantum mechanics, until we open the box and observe, the cat is both alive and dead at the same time, existing in a superposition of states. Only when we observe the cat does it collapse into one state, either alive or dead. This is similar to how quantum particles behave. They can be in multiple possible states at once until they are observed or measured. These strange behaviors of quantum particles aren't just academic. They have practical applications that are becoming increasingly important in modern technology. For instance, quantum computers take advantage of superposition to perform calculations far more efficiently than classical computers. In a classical computer, data is processed in bits, which are either 1 or 0. However, in a quantum computer, data is processed in qubits, which can be 1, 0, or both at the same time, thanks to superposition. This allows quantum computers to solve complex problems, like those in cryptography or simulations, that would take classical computers an impractically long time to handle. Speaking of cryptography, quantum cryptography is another exciting application of quantum mechanics. Unlike classical cryptography, which can be broken with enough computational power, quantum cryptography uses the principles of quantum mechanics, specifically the behavior of photons, to create nearly unbreakable encryption. Since the act of measuring or intercepting quantum particles changes their state, any eavesdropper trying to intercept a quantum-encrypted message would reveal themselves by disturbing the system. This offers a new level of security that could be essential as quantum computers become more powerful. Semiconductors, which are crucial in modern electronics, also rely on quantum properties. Quantum mechanics allows us to understand and control how electrons move in these materials, making devices like transistors, which are at the heart of smartphones and computers, possible. Without the quantum behavior of particles, much of the technology we use daily simply wouldn't exist. There's also another quantum phenomenon called quantum teleportation, which sounds like something out of science fiction. While it doesn't involve teleporting physical objects, scientists can use quantum entanglement to teleport the quantum state of one particle to another distant particle. This is already being tested for use in quantum communication systems. The quantum world is not only fascinating for its strange and counterintuitive behaviors, but it is also becoming incredibly useful in advancing technology. From quantum computers that could revolutionize industries by solving problems currently beyond our reach, to quantum cryptography that provides unprecedented security in a world of growing cyber threats, and semiconductors that power our daily lives, quantum particles are playing an increasingly important role in our future. In conclusion, the quantum realm is mysterious and often difficult to wrap our minds around, but it offers incredible possibilities for technology and our understanding of the universe.